I'm still forgetting. Where was I? Right. So in terms of a graph, just looking at the exact same graph, you can draw it in multiple different ways. Actually, almost everybody in our course could draw it a different way, have a different picture associated with the graph, simply by putting the vertices in different locations on your piece of paper when you're drawing the graph. Okay? Now, that being said, if you're given the graph, the picture of it, you want to know if you actually started with the same underlying structure. You actually had the same vertex set. You had the same edge set there. In those situations, it still can take a little work to make sure all those pictures are the same, really correspond to the same graph. But what happens if you had one step further where the labels on your vertices were different? And we did the theoretical last time of maybe in one graph all the vertices were labeled with letters, and in the other graph all the vertices were labeled with numbers. You didn't have any of the same labels, but maybe you still had the same underlying structure, and somebody just taken the first graph, erased the A, B, C, and replaced it with 1, 2, 3, etc. Okay? So that's the motivation behind dealing with are graphs isomorphic or not, because isomorphic graphs are two graphs that their pictures look identical as long as you ignore the labels. That being said, the quote-unquote identical part, you have to check it because it's not quite as straightforward as checking to see if the picture is exactly the same. Now, when we define isomorphic graphs, we always define them by way of isomorphisms, and no, there's not really a great way of defining isomorphisms. There's very, very precise ways of finding isomorphisms, and what you see in front of you right now is one of those precise ways. And I'll also rephrase it in terms of what you would sort of layman's terms, okay, which is not a precise definition, but gives you the right idea. So officially, an isomorphism is a type of function. It's a one-to-one correspondence. So that means what happens is you're going to take all of the vertices in one graph, and you're going to map them, or you're going to assign them to exactly one of the vertices in the other graph. Okay? Now, this function works specifically on the vertices. So what you're doing is you're not just converting all the labels on your vertices in one graph into all the labels of the vertices on the other graph, but you are also preserving your edges. So when you change the labels of the vertices on, say, this first graph, and you had an edge between some pair of vertices that you just swapped out their labels with the labels from the second graph, you're still going to keep that edge. That edge won't disappear when you get to the second graph. Okay? Now, all this being said, you can actually ignore isomorphisms a little bit, just a little bit, by remembering the following thing about isomorphic. Roughly speaking, well, I shouldn't say roughly speaking, the official definition is two graphs are isomorphic if there exists an isomorphism between them. Okay? It doesn't have to be one isomorphism. There's typically multiple isomorphisms that'll work. If one exists, you normally have several. Okay? But in terms of layman's terms, what does this mean? This basically means you can take graph number one, relabel your vertices appropriately, maybe move some of the vertices around so the picture actually changes shape a little bit, and you will be able to build or recover that second graph. That's roughly speaking what's going on here. Okay? Now, all that being said, it's way easier to tell what's going on once we start getting into examples. So the majority of this section 1.2, which is where isomorphisms and isomorphic graphs are located in your textbook, the majority of this section is just going to be a lot of different examples of different situations and what you would need to do in different situations. One of the big things that we'll do is we'll also talk about how you decide to do which technique and when, okay? Because there's actually a hierarchy. And we started to get into that hierarchy last time, and that's what we ended on. So symbolically, two graphs are isomorphic if they have this little symbol. It looks like an equal sign with a little squiggly thing on top, or a tilde. And that means basically they're the same graph. The tilde on top tells you they're not exactly the same because maybe their labels are different on the vertices. Now, in terms of what you automatically get from the way of the definition of an isomorphism, or an isomorphism existing between two graphs, the one-to-one correspondence part of the isomorphism means automatically you have to have the same number of vertices between the two graphs. That's low-hanging fruit. If you're checking if two graphs are isomorphic, if they have a different number of vertices, bam, there's no way it's really the same two graphs, but one's a disguise of the other. Okay? Same deal, the isomorphism is supposed to preserve edges. Specifically, the edges are between the same corresponding pairs of vertices across your two graphs. So that means you have to have the same number of edges between the two graphs or in each of the two graphs. So if you have two graphs and one of them has, say, 10 edges and the other one has 9 edges, they are not isomorphic. That's no way possible. Now, here's the extra bit. Every single vertex in the graph will also keep its degree. In other words, if you have, say, vertex A in the first graph and it corresponds to vertex 2 in the second graph, the degree of both A and 2 have to be the same, and that's because the degree counts how many edges touch vertex. So if the isomorphism preserves where the edges are, that means the degrees will be the same. And this part right here, this is where the wild, wild west starts happening. After you've confirmed that you've got the same number of edges between your two graphs, you've got the same number of vertices, and all the vertices have the same degree. In other words, you have one vertex of degree 1 in the first graph, you have one vertex of degree 1 in the second graph. In the first graph, you have 3 vertices of degree 2. Other graph, you have 3 vertices of degree 2, and so forth. And we'll see that in our very first example, actually. I think in all of our examples, we'll actually go through these guys. After you've exhausted these 3 guys, if everything still matches, then you start looking at your other properties. And roughly speaking, this is normally the order in which you look at them. You typically start looking at subgraphs and see if the subgraphs match, and we'll have examples of what that means. You look at, are there any paths or cycles, trails, circuits, etc., something that's that's unique about your graph, and you check to see if it's then in the other graph. You look to see what's going on with the complement graphs. We haven't defined that yet. We'll define what a complement graph is when and if we need it. And then you check to see, hey, if one of our two graphs is a special type of graph, like a bipartite graph, well, the only way that they're really the same two graphs in disguise is if the other graph is also a bipartite graph. So you start looking at all the different properties you could possibly look at. Okay. Now, these are the things that you will automatically get if the two graphs are isomorphic. In other words, everything matches. But if you're trying to figure out if your two graphs are isomorphic or not, in other words, you don't know yet, this is how you deal with that. This is the strategy that you would employ. If you have no clue if the two graphs are isomorphic or not, or you suspect that maybe they're not isomorphic, you're going to check through all the properties. The first thing that you check in that list, number of vertices, number of edges, then you look at degrees, then you start looking at the more obscure properties. If any of the properties don't match, automatically you're going to get the two graphs are not isomorphic. You're done. As soon as you get some property that doesn't match, stop. Graphs are not isomorphic. However, if all the properties are matching across the two graphs, they're exactly the same across the two graphs, that actually gives you absolutely no information. All that tells you is either, you have two options, either the two graphs are isomorphic, or you just haven't found a property yet where the two graphs don't match. Okay? So every time something works, you move on to the next thing to check until you get a pretty good guess that, hey, you know what, maybe they really are isomorphic. Once you suspect that the graphs actually are isomorphic, the only way to confirm that is you have to actually build that function, that isomorphism. So for us, in terms of needing the isomorphism, needing that function, that's when we get to this point where we think we actually have two graphs that are isomorphic, we're going to have to build an isomorphism. Okay? So that's where that function comes into play and where you have to know about it. So let's jump into an example. So suppose you have the following two graphs. Give you guys a second if you want to copy them down. And I'm going to go ahead and call them G and G prime. It's standard to call the two graphs G1, G2 like we did before, and in some of the future examples I will. But it's also really common to call them G and G prime. Please note the prime does not in any way, shape, or form indicate derivative. This is one of the things that you do in the area of discrete math, that you go and you put a prime on one of your symbols, and it means this guy, we're going to talk about him at the same time we're talking about regular G, and we were too lazy to come up with a new name. Okay. Now, when we go through this guy, if we want to determine whether those two graphs are isomorphic or not, oh, hopefully that didn't go crazy on you. I think it did. Okay. It went crazy on me for a second. What we're going to do is we're going to start with the easy thing. So the easy thing we're going to start with is we'll go through and check to see, all right, well, do we have the same number of vertices? Do we have the same number of edges? And I'll do something on this particular example that I won't do on the other examples. We'll go ahead and actually list out what the different vertices and edges are. But while we start to do that, what do you guys think? Does it look like we have the same number of vertices and edges? I'm getting my windows back in order here because they just went haywire on me. That way I can see if you ask questions. Yeah, so these two guys actually do have the same number of vertices, same number of edges. So for G over here, we've got, what is that, five vertices. If we actually wrote out the vertices, this would just be those letters A through E. If we wanted to go ahead and, actually, let me go ahead and just make that screen a little bigger for us. If we wanted to look at the number of edges, did anybody count up the number of edges? Oh, I really don't want to write out the number of edges. Oh, we'll do it. 7? Yeah, that looks like 7. So one of them is AB. We also have AC. We also have AD. If we look at B, we already have BA, so we've got BC, BD. We start at C. We already have CA and CB, so we have CD. And the last one is DE. Now, if we do the same thing in the second graph, what happens here, the vertices are even easier to count. We've got 5 vertices. The only time when you label vertices with numbers and it's not easy to count is if you skip a number, or maybe you don't start with 1. So here our vertices are simply the integers 1 through 5. And then we'll do the same thing with edges. Double check, does it look like there's still 7 edges over here? So far we have 3 edges that have 1 as an endpoint. If we look at 2, we have 2, 1, 2, 3, 2, 4. Skip 2, 1 because we already had it. We start with an endpoint of 3. We have 3, 1, got it already. 3, 2, got it already. 3, 4. And the only guy left then is 4, 5. So yep, we still have 7 over there. And you guys already said it looked like they had the same number of vertices and edges. So at this point, here's the conclusion we can draw. Maybe they're isomorphic, maybe they're not. That's as good as we've got. Okay? So the next thing that we want to do is we would then say, all right, well, maybe we can tell something if we look at the degree of each of these vertices. And if we look at the degree of each vertex, I'm going to go ahead and just put it in a chart. So here's our vertex. Here's our degree. Here we have 5 vertices. And then we'll just need to find the degree of each one. So the degree of A, B, and C are all what? Yep, they're all 3. What about the degree of D and E? Yep, 4 and then 1. Perfect. So if these two graphs are isomorphic, that would mean we have to have in the second graph 3 of the vertices having degree 3, 1 vertex with degree 4, and 1 vertex with degree 1. So let's see if that happens. So here our vertices are 1, 2, 3, 4, and 5. Right? So in this case, the degree of 1, 2, and 3, any guesses what those degrees are? Yep, those guys all have degree 3. And the degree of 4 and 5 are going to be what? Yep. So just looking off of this information so far, this tells us that, hey, there's definitely a potential that these two graphs are isomorphic. Okay? It actually turns out in this particular case that these two graphs are isomorphic, and if we kept looking further, everything was going to match. Okay? Now, when you get to this point, if you have a relatively small graph, one of the ways to check to see if it's isomorphic is you start checking to see if you could pull some of these vertices around, sort of visualizing in your head, if I move these vertices, could I actually get this shape? Now, notice one of the difference between the two graphs. This graph, none of the edges are crossing. In this graph, two edges are crossing. So one of the things you might do is you might say, hey, you know what? This looks like maybe I need to, I don't know, move vertex B in the middle here. That would make it not crossing. It wouldn't look like this graph yet, but maybe it's closer. Okay? So let us see at this point if we can find an isomorphism. Okay? So far, everything is matched. There's the potential that we may have an isomorphism. And just so we can see the pictures of the graphs just fine, I'm going to go ahead and write our guess for our isomorphism over here to the side. There are multiple ways that you can write an isomorphism, and if you look at it in your textbook, your book does not write it this way. But I find for most people, especially if you've never done this before, this is the easiest way to write your isomorphism or your one-to-one matching. I like to write it in some sort of a chart. I normally write it in something that looks very much like a T-chart, so 2 columns, but you don't have to. Some people like to write it sideways, more like what we did with the vertices in the degree chart. Okay? You then pick on one of the 2 graphs. It doesn't matter which one. I'm going to pick on graph G because it's the first one, and you write down all the vertices. Okay, so this is just the vertices A, B, C, D, and E, and I'll go ahead and extend that line. Then you look at the information that you have. Hint, up here, all this tells you is it's possible to match things. Down here is where you're going to have some information that you can use. And you say, all right, well, based off of the information that I've calculated so far, whether it's as little stuff as we've done in this example, or whether it's more like we'll do in the future, you start saying, all right, well, if I look at my vertices A through E, are there any vertices that are forced to be mapped to any of the vertices 1 through 5? Anybody have a guess on if there's any vertex that's forced to be matched? Yes, and you guys nailed it, those of you who sent in answers. If you look down here at D and the E, those 2 guys are completely determined. D has to match to vertex 4, and E has to match to vertex 5. Why? Because those guys are the only vertices in the 2 graphs that have degree 4 and have degree 1. So if vertex D is the only vertex in the first graph with degree 4, it has to be matched to that one vertex of degree 4 in the second graph. Okay? Now, that being said, so that's what these 2 guys are. That being said, anybody have a guess on who we can map A, B, or C to? Sure, we could totally say B is 1. And if you want B to be 1, anybody have a guess for what you want A to equal or A to correspond to? True. So which one do you want me to write down? Sure, let's go with 3 and 2. It's going to turn out that you can put 1, 2, or 3 in any order you want. Okay? So when we go back, let's check to see if our current isomorphism works. Here's how you check to see if it works. And let me do a different color so you can see the scratch work. What color? I think green will probably work. So what you do in checking is you go and you focus in on one of the 2 guys. Well, we started with G when we wrote down all of our vertices, so let's pick on G prime over here. And what we're going to do is we're going to replace all of the A's in our vertex set with, in our edge set with 3's. Then we're going to replace all the B's with 1's. Then we're going to replace all the C's with 2's, D's with 4's, E's with 5's. Okay? There's only 7 edges. It won't take forever. So we have any 3 is going to be replaced with an A. So this guy would be an A, 3, 3, 3. This guy would be an A, 3, 3, 3. This guy would be an A, 3, 3. Those are the only 3s. So we've got A's taken care of. We'll then go back and replace any 1s with B's. There's a B, there's a B, there's a B. 1s, 1s, 1s. Those are all the B's. Then we go and replace any 2s with C's. So there's a 2, 2, 2, 2, 2, 2. There's a 2, 2, 2, 2. There's another 2. That's the last 2. Then any 4 we'll replace with a D. So there's a 4. Second line, there's 2 4s. Last line, there's also a 4. And any 5s we'll replace with an E. Now, here's the thing you check after you do all this scratch work. You check to see if each one of these edges with now those labels of A through E match exactly to the edges you were supposed to have back in graph G or the other graph. So BC, BC. We have a BC right there. The next one is AB. We have an AB as our first edge we listed. Then we have a BD, BD, BD. BD is second row, middle. CA. CA isn't written in that order, but we do have an AC, which we know with undirected edges is the same thing. Then we have a CD. CD looks like it's in the second row right here. Next, we have an AD. That looks like it's the end of the first row. And the last one, we have a DE, which is exactly the same as our last guy that we had written before. And that's how you verify that your isomorphism actually is an isomorphism. In this particular case, right here, there's actually 6 different isomorphisms that will work because these set of 3 vertices, you can shuffle them up in a bunch of different orders. Kind of makes sense, a little bit makes sense, at least so far. All right, so before we go on to our next example, I have something for you guys, and I'm going to go ahead and share it with you. So let me move this off that window so you can actually see it. This is now active. You guys should be able to see it, and I'm going to stop sharing the other window. That way you can see it in a little bit larger screen. So this is now a question thrown to you. It's totally just a multiple choice question. It's not going to ask you to build the isomorphism whatsoever. But the claim here is that you're given a graph, and this looks different when you pull it in. I demoed that last night. Quite a bit different. Luckily, these guys are a little bit bigger from what I saw. You're given some graph, and we'll call this graph G right here, that looks like a bunch of lines. Okay? So it's a little bit bigger than the graphs we just looked at. And the claim is it is potentially isomorphic to one of these 3 graphs. Okay? So what I'm going to do is I am going to throw you guys into groups. That way you can talk about it and not try to do it all on your own. And see what you guys think. Are any of these graphs potentially isomorphic to this guy over here? Okay? So any questions before I throw you into the groups? Everybody got the question up where they can see it so they can see the graphs? Are the letters keeping the same degree? If they're isomorphic, you would have to have the vertices correspond. In this particular case, I didn't actually create these graphs. If I had, I would have changed up the vertices. The person who created these graphs uses the same letter set for labeling all of these vertices. So that part is a little bit awkward, I will agree. When you're done, yes, if you don't mind terminating your group, that would be amazing. That way I know when you guys have finished in your group. All right, I don't see any more questions from you guys, so I'm going to go ahead and throw you into the groups or the breakout sessions. That will be starting in 3, 2, 1. Here they go. For a subgraph, we've looked at this before. What was it? It was where you build a new graph where all the pieces and parts of the new graph, both the vertices and the edges, have to only come from your, it's not called this, but essentially your parent graph, okay? So in this example right here, to demonstrate, we had some graph G, relatively straightforward graph. We had 5 vertices. We had, what is this? 1, 2, 3, 4, and 5 edges. And a potential subgraph here is took 4 of those vertices, so everybody except for vertex E, and then we went ahead and took 2 edges. Okay? And we talked about that last time, but to remind ourselves of that. This is something that you can actually look at inside of graphs that are a little bit more complicated, and you still want to know if those a little bit more complicated graphs are isomorphic or not. And then it froze on me. That's always fun. All right, so a couple of other things to remember about subgraphs. First of all, if you pick any graph on blank or n number of vertices, it is automatically a subgraph of our complete graph. And remember, our complete graph, the symbols for that were Kn, because Kn was what? It was all the possible edges on n vertices, excuse me. So if you pick any graph on n vertices, maybe it is a complete graph, but even if it's not, if it has fewer edges, then what happens? Well, it's just a subgraph. Okay. So what does this mean in terms of isomorphic graphs? If you have 2 isomorphic graphs, you pick some subgraph of the first graph. Then, if the 2 original graphs were isomorphic, you have to find a subgraph inside of your second overarching graph, G2, and I'll be lazy and call it H2. That H2 and the original subgraph are, in fact, also isomorphic. Now, what's the advantage of looking at subgraphs? The advantage of looking at subgraphs is they are often smaller in some sense than your original 2 graphs, which means they are potentially easier to check if the 2 graphs are isomorphic, or the 2 subgraphs, excuse me, are isomorphic. If the 2 subgraphs are not isomorphic, that automatically tells you, if these guys are not isomorphic, that tells you that the overarching original graphs are also not isomorphic, and that's where it's useful. If the 2 subgraphs are isomorphic, all that tells you is maybe the original graphs were isomorphic, maybe you just haven't found the property where they're different. So, suppose you have these 2 graphs, okay? So these 2 graphs both look very boxy to me, sort of a 2-dimensional rendering of a box with some missing edges, okay? So suppose you have G and G prime, and it looks like I forgot to label the graph G and the graph G prime. So let me go ahead and label these guys. I put G typically over here on the left, and G prime typically over here on the right. All right. Now, if we want to check to see if these guys are isomorphic, don't overtax your brain. First thing that you want to do is you want to check to see, do they have the same number of vertices? Do they have the same number of edges? So what do you guys think? How many vertices do these graphs have? And do they both have 8 vertices? Yeah, they do. So first, quick check means potentially these guys are isomorphic. And 10 edges, yes. And they both have 10 edges. So first 2 quick checks, potentially they're isomorphic. Third thing you always check is you check their degrees. Okay? So if we look at the vertices in the first graph, I'm going to be lazy and just write it with a V for vertex since we have 8 of them. And then we're going to have degrees below here. So this is A, B, C, D, F, G, H. Don't forget H. Okay? So the degree of A should be what? Was that 3? Yep. What about the degree of B? Yep. How about the degree of C? Yep. How about the degree of, where'd it go? D. Back to 2. Now how about the degree of E? Yep. How about the degree of F? Yep. How about the degree of E? No, we already did E. How about the degree of G? Excuse me. Okay. I don't know. I almost misread it. Just a second. And lastly, how about the degree of H? Perfect. So notice something that's different about this graph than the graphs we had in the last example that we did together. In the last example, or really the first example that we did together, we had what? We had a bunch of degree 3 vertices. We had exactly 1 degree 4 vertex and exactly 1 degree 1 vertex. do we have any vertices in here that have a degree that's unique? In other words, only one vertex has that degree. Correct. So we don't have anything like that. We only have degree 2 and 3 vertices, and we have at least 2 of each. Actually, do we have 4 of each? It looks like we actually have 4 of degree 2 vertices and 4 degree 3 vertices. That actually is a pain in the butt. Okay? Why is this potentially a problem? Because it doesn't give you an immediate idea of what sort of isomorphism you would create. So even if we suspect that these two graphs are isomorphic, we would need more information than just their degrees to figure out what that isomorphism actually is. So we're not going to be able to attack this problem exactly the same way we did our first example. But that being said, let's do a quick sweep. Maybe the degrees aren't half and half of degree 2 and degree 3 in the other graph. And if that's the case, immediately the two graphs are not isomorphic. All right, so if we look at, how about the vertices around the big outside looking square? If we look at vertices 1, 2, and 3, what are their degrees? Yep, so the 1 and 2 both have degree 3, 3 and 4 both have degree 2. And let's do the same thing with vertices 5, 6, and 8. What do you guys think? What would be their degrees for vertices 5 through 8? Ooh, the order isn't exactly the same. Oh, I lied. I went around backwards. You guys are totally right. I normally write the labels of the vertices clockwise instead of counterclockwise, and I was reading it, not looking at the labels. Don't do that. Look at your labels. All right, so conclusion here. Do we have the same number of degree 2 vertices across the two graphs? Do we have the same number of degree 3 vertices across the two graphs? We do. So the conclusion we should reach at this point is maybe these guys actually are isomorphic, but we don't have enough information to actually create an isomorphism yet. So this is where both with looking ahead to potentially having to create an isomorphism and also looking ahead to saying, well, maybe we just haven't found the property where these two graphs differ, we're going to need to do another technique, okay? And this is where in our strategy that we had a while back, we said, hey, we just need to look at a bunch of different properties, okay? And in this particular case, I'm going to focus in on the degrees, okay? So if we wanted to try to build our isomorphism, and I'm going to come at this from the standpoint of attempting to build an isomorphism, all of the degree 3 vertices, so in the first graph that's A, C, E, and G, and all of the degree 3 vertices in the second graph, so that's 1, 2, 5, and 6, have to be mapped to each other. Now, we don't know what order that they should be mapped to each other, but we know that that subset of vertices has to correspond. In a similar manner, you can do the same thing with degree 2 vertices. If you look at the 4 degree 2 vertices in the first graph, so that would be B, D, F, and G, not G, F and H. They have to be mapped to the degree 2 vertices in the second graph, so that's vertices 3, 4, 7, and 8. Again, that's 4 guys mapping to 4 guys. We don't know what order in which they need to be mapped from. Maybe it doesn't matter and you can interchange them, but more likely how you map that subset of degree 2 vertices from one graph to the other graph will actually matter. So because of that, what I want to do is build a special subgraph. Okay? And this is why we refreshed on the definition of a subgraph just a second ago, and that is because I'm about to use it for this one. Could you deal with paths in this case, as one of you asked a while back? Yes, you could. I personally think dealing with subgraphs is easier than dealing with paths, but again, it depends on what's easiest for you to spot. There's always more than one way to approach whether two graphs are isomorphic or not. And when I say more than one way, that's after you've done those 3 steps. So this is always the first things you check. Then after this, all of you could check almost something different at this stage. But I would recommend if you have huge groupings or a large number of vertices that have the same degree, look into subgraphs. Okay? So let me actually label what we did. So this is like, oh no, I did not want that to be highlighted. I forgot I was still on highlighter. So this is like a first step to check the number of vertices and edges. Getting degrees is like your second step. So third step that you would do is checking subgraphs. So we can look either at degree 2 vertices or degree 3 vertices. Do you guys have a preference? Hint, it doesn't actually matter. Sure. Degree 3 guys are the ones highlighted, so that actually made sense in what we've done so far. So here's the key thing. We want to look at all, and that's the part that's critical, all of the degree 3 vertices. And we're going to do this in both of the two graphs. If you look only at your degree 3 vertices, we're going to use those vertices, the 4 of them, and build an appropriate subgraph. So let me scooch up so we can actually build that subgraph. So let me label this to get a subgraph. Now we're also going to go ahead and include all of the edges possible corresponding to those vertices. So we said vertex A was degree 3, so I'm going to go ahead and write down A. We said vertex C is also degree 3, so I'm going to write down C. We also had E. Where does E live? Oh, I already did E because I misread my own handwriting. That's embarrassing. We have E, C, and G. So those are the ones in a line. There's G, and there's C. Okay. Now, once you have all of your degree 3 vertices, and I like to on purpose put them in the exact same orientation as the original graph. No, you don't have to do that, but you do now need to include all of the edges that you still have both their endpoints in this subset of vertices. So A was originally degree 3. Notice, though, the edge A to D no longer exists because D is not in the subgraph. Similarly, A to B is not going to be included in the subgraph simply because B isn't in our subset of vertices. However, AE right there will be included because both A and E are both degree 3. So then if we look down here at E, if we look at all the edges that are incident to E, we've already got AE. EH won't be included because H isn't in this subgraph. EF also won't be included because why? Well, F's also not in the subgraph. You guys spot if there's any other edges that we need to put in this subgraph. Yep, there's exactly one more, and that would be GC. So that takes care of, and let's go ahead and label it. I'm going to go ahead and label this guy H for a subgraph. And if we wanted to label the vertices and list them all out, we could, but since we already highlighted our degree 3 vertices right up there, I'm not going to worry about it. Now over here on the second graph, let me go ahead and label this one also with an H but a prime. I did the prime there to match the notation that we did with the original graph. In this case, we're also going to pick on our degree 3 vertices, so we're going to look at vertices 1, 2, 5, and 6. And 1 is up there in that top left corner, 2 is bottom left corner. Where's 5 and 6? In the middle, also on the left. So here's 5, and here is 6. So then at this stage, you say, all right, well, are there any edges that we should include or we must include? In other words, we have to include all of the edges that are from the original graph where both endpoints are in the set of vertices 1, 2, 5, and 6. So does anybody spot an edge that we need to include? Well, we can't include all 10 edges. So when you mean all edges, I think you mean something else. So 1, 2, yes. How did the other easy one, 5, 6? Anybody spot another one? 1, 5, and 6, 2. Are there any other edges? In other words, did we miss putting in any edges? Yep. So in this case, we grabbed all of our edges. Now, looking at these two subgraphs, what do you guys think? Are those two subgraphs isomorphic? Now, what's nice about having this smaller picture where you have only 4 vertices? What made it easy to see that those two guys were not isomorphic? Again, don't overthink it. Ooh, yeah. Yes to both of those things. Ooh, yes, that too. So there's actually a bunch of different things you can say. One of you said that H here disconnected, but H prime is not disconnected. Yes, if you have two different types of graphs, they would not be isomorphic, so that's a great thing to notice. Different number of edges. Over here in H, you have 2 edges. Over here in H prime, you have 4 edges. So that's a quick check. Definitely not going to be isomorphic. And I think there was another one I saw. Degrees. Yeah, your degrees are also different. Here, all 4 of these vertices now have degree 1. But over in H prime, all 4 of these vertices have degree 2. So all 3 of those different reasons are a really quick way to show that their 2 subgraphs are not isomorphic. So let us put in the conclusion. Okay, so conclusion. Wow, I can't spell a U. Let's pretend I can spell letters today. So H and H prime are not isomorphic. And we said that that was because they had a different number of edges. We also said that we looked at disconnected versus one was connected. And we also looked at their degrees, so different degrees, all of which are good things to look at. But you only really need, as soon as you spot one of those, you don't have to look any further. Now, since the subgraphs were not isomorphic to each other, and notice, it's not that you picked any old subgraph. Because we picked all of the degree 3 vertices in the first graph, we had to, if the original 2 graphs were isomorphic, we had to be isomorphic to the corresponding subgraph in the second graph. Why? Because we knew that A, E, G, and C had to be mapped to 1, 2, 5, and 6. Because we knew all of these guys had to correspond to all of those guys, there is no other option for this subgraph H to be isomorphic to any other subgraph in G prime. So we forced that these were the 2 subgraphs that must and could only be isomorphic, as in that there were only 2 subgraphs that could possibly be isomorphic when we looked at the degree 3 guys. Okay? So since they were not isomorphic, what that tells you is that there is no other subgraph in graph G prime that subgraph H is going to be isomorphic to, which means that the original graphs of G and G prime, there's no way that they are going to be isomorphic, because if they were isomorphic, we could find some subgraph in G prime that was isomorphic to H. Okay. So that is why we picked all the degree 3 vertices. It was this forcing that checking, hey, I know that this is the one and only subgraph that could potentially work. Okay. Now, what happens if these 2 guys had been actually isomorphic to each other? If they'd actually been isomorphic to each other, it gives you absolutely no information whatsoever, but it would have given you a little bit of information how to potentially build your isomorphism. As in, if these 2 guys looked exactly the same, you'd say, hey, maybe A would have to map to whichever guy also looks on the other endpoint of its own little edge. Okay. But once you get to this conclusion that your 2 graphs are not isomorphic, stop. That's the end of that problem. Now, that's it for that example. Yes, so that is correct. So the question is, the only time when you would worry about doing this subgraph technique is if you have 2 or more degrees that are the same, and that is true. And in fact, if these 2 subgraphs have been isomorphic to each other, your next thing that you might do is check all the degree 2 guys and look at those subgraphs. Check to see if the subgraphs built from degree 2 guys were isomorphic or not. But yeah, if you only have 1 vertex of some degree, you're not going to be doing a subgraph in that particular case. And quite honestly, if you only have 2 vertices of a specific degree, you normally don't do subgraphs. It's typically when you have 3 or more vertices of a particular degree. And honestly, it's when you have very few different types of degrees and a relatively large percentage of your vertices match in degree is typically when you use this technique. And I know that was probably way more information than what you wanted, but hopefully that made sense. Other questions about what we did with this example before we move on? All right. So the next example that I've got for us is, notice the directions are exactly the same to pretty much every example that we've had today, except for the one that illustrated subgraphs. In this particular case, we've got two graphs that are, I'm not going to lie, I almost always mess them up, so I was very careful to do them before class so they would look less wonky than normal. Apparently, I'm bad at putting vertices in a circle. So in this case, I went back and called the two graphs, the two original graphs, G1 and G2. They both look very similar. All of their vertices are oriented in a circular orientation. They both have a bunch of edges. They've got edges that are around the outer perimeter, so it looks kind of like a seven-sided polygon, the one that actually has two names, heptagon or septagon. And then it's got they've got a bunch of edges which looks like they're inside of that polygon. Okay? So if we wanted to check to see if these guys were isomorphic or not, in this case, our first step we want to do is the same first step you basically always do anytime you want to check to see if two graphs are isomorphic, especially if it's not really obvious from first glance. Notice the subgraphs were pretty obvious from first glance that they were not isomorphic. So first up is you check the number of vertices, the number of edges. In both cases, we have 7 vertices, and the only thing that's going to take a little bit of work is counting up the edges. Anybody happen to count up the edges so far, or yet? A little bit fewer than that. But I'm not going to say that is a very reasonable guess. One of the ways to grab the number of edges is take the degree of each vertex and notice the degree of all of these vertices is. Anybody spot what the degree of all the vertices are across both graphs actually? Yep, it's 4. So you multiply 4 times 7, you got the 28, divide by 2, overcounted it by counting it by each endpoint. Happens all the time. If you try to count it by hand though, that's where you can start losing count. All right, so once we establish that they have the same number of vertices and the same number of edges, and quite frankly, for most of the examples from here on out, we'll probably have the same number of vertices and the same number of edges, at least when we're talking about it together in class. The next thing we want to do is we want to check the degrees of all of these guys, and we actually already said that all of them had degree 4. So all vertices, wow. T's are not spelled like that. All vertices are degree 4, and that is true of this second graph as well. Now, question for you. Would looking at a subgraph, like what we did in our last example, actually help here? Anybody have a guess? They are actually not both K4. In terms of subgraphs, unfortunately not. The only time when subgraphs are helpful is you do want to have a very high percentage or a relatively high percentage of vertices that have the exact same degree. We definitely have that. But if we actually pick all of the vertices of degree 4, your quote-unquote subgraph is what? Your subgraph would actually be the original 2 graphs, and that's not helpful because the whole point of subgraphs was to get a new graph that was smaller and easier to work with. So in this case, not helpful because all the degrees are the same. So let me put that comment in here. So because all vertices have the same degree, using that technique of grabbing your subgraphs won't help. And that is because the subgraph you want to grab is a subgraph of all vertices of the same degree. So turns out in this particular case, Or what you often will look at next is something called a complement or a complement graph. Okay? Now, we haven't defined that yet, so let us do that. Okay? So a complement of a graph goes as follows. You start off with some graph. So you've got this graph that we'll call G. It's got some set of vertices. It's got some set of edges that builds it. Okay? Then the complement of that graph is, in terms of symbols, it looks like the same symbols you would use in sets. You just put the line on top of the original name. So the complement of G is, well, you use all the same vertices, those don't change, but you complement the edges. Now, complementing the edges just seems crazy, stupid, and weird, but what that actually means is you take your complete graph on the same number of vertices. So let me go ahead and comment this, and let me put it in a slightly different color so we know it's a comment. That microscopic symbol was the number of vertices. So you look at the complete graph on however many vertices you're currently dealing with, and you remove all of the edges from the complete graph that were in G. So let's do a baby example to make sure we're on board with this. Okay? So suppose you have this guy. It's just 4 little vertices right here, so A through D. If we want to find the complement of this guy, and let me go ahead and label it G, that way we can put some symbols on here later. The first thing that you would do, and I'll be honest, this is something you would do the first couple times you complement your graph, and with smaller graphs, as you go forward, you'll do this middle step less and less. So first thing I'm going to do is I'm going to write out the complete graph on 4 vertices. I'll go ahead and label the vertices the same as the labels in the original graph G. Okay. Well, K4 is all possible edges. So this guy is going to look like a square with then 2 extra lines. So it looks like an X inside of a box. Okay. Or a square with all of its diagonals. Now, next thing that you do is you check and you see, all right, well, where are the edges that are currently in G? Okay? Well, the edges currently in G are AB, they are B to D, they are B to C, and they are C to D, and I accidentally drew those last ones in the opposite order. Okay? I highlighted that just for scratch work. Now let's make sure that isn't a highlighter. So what this tells us is that our actual complement, so G complement, is going to be vertex set is identical the same, so we still have A, B, C, D. But when you go over here to our reference graph of our complete graph and for vertices, you're only going to pull the edges that were in G. So you're only going to pull the non-highlighted edges. So that will be A to D, and that will be A to C. That's the complement. Notice something that automatically happens here. Your vertex set stays the same. The original number of edges in G was 4. The number of edges in our complete graph was 6. Anybody notice how many edges are in the complement graph? Anybody notice a relationship where that 2 comes from? You got it. The total possible edges from the complete graph minus the number of edges in your original graph G. And that is a way to check to see if you actually have the correct number right there. Okay? So that's the idea behind the complement graph. Now, in using the complement graph for checking if 2 graphs are isomorphic, the only time when the complement graph is going to be useful is if the complement is simpler or easier to deal with than your original graph. In other words, you want to have fewer edges than in the original graph. So that means the number of edges in your original graph needs to be bigger than, larger than, more than half of the number of edges in your complete graph. So when to use this complement would be when you're over that halfway point in your number of edges. Now remember, we talked about the number of edges in a complete graph. So in a complete graph, the number of edges equaled n times n minus 1 over 2. So in terms to use the when to use the complement, if your number of edges in the original graph, let's put a little g here at the bottom, is greater than or equal to half of the number of edges in the complete graph. That would be the check. Okay. Now, you can also visibly do it. Here's how you do the visible check. Oh, I've got an extra question there. The visible check, for example, on this one is, does it look like we have a bunch of edges? Does it look like this might be close to the number of edges that you might have in the complete graph on 7 vertices? The answer is actually yes. You got a bunch of edges in here. That means doing a complement might be helpful. So we're going to do that, but it looks like I've got prepped up one little example before we do that, and then we will jump into going back to the example of isomorphic graphs in just a second. Okay. So suppose you've got this guy, and this is actually an interesting example. Anybody have a guess on what the complement of the graph that looks like a Z would be? So it's still 4 vertices. It's still vertices A, B, C, D. I was too lazy to change that. The edges are A to B, B to D, and D to C. Ooh, I like how some of you guys answered that. So you'll still have the vertices A, B, C, and D. You won't include AB. You will include AD and AC. I'm just going off of the edges incident to A. If you look at the edges incident to B, B to A, B to D are in the original graph, so we don't include them. But you do include B to C, and it turns out all the other edges in the complete graph are already used in the original graph. Yes, it would totally look like a capital N or that Z rotated, which means, interesting fact, in this particular example, wow, why did I do the slash? In this particular example, G and its complement were actually isomorphic. Yeah, so in this case, you'd say it's isomorphic to itself, or its complement is isomorphic to itself. This is one of the rare cases where that happens. The only time that that can happen is if the original number of edges is exactly half the number of edges from the complete graph and the same number of vertices. And here, technically speaking, you would definitely need to call this isomorphic, not equals, because in the original graph, you had the edge AB, and in the complement graph, the edge AB is missing, so you actually have to relabel. Awesome. Maybe my cable just wiggled a little bit, or on your end, if somebody else could hear me. Awesome. All right. But yeah, the point of that example was to say, hey, sometimes you actually get the complement is isomorphic to the original. Don't freak out if it happens. It does happen on rare occasions. All right. So we actually already talked about this property, and the property that's actually amazing about complements is it's even better than dealing with subgraphs or degrees. It is, if you have two graphs that are isomorphic, this is only going to occur if their complements are also isomorphic. So in terms of checking, if you get the two complement graphs are isomorphic, bam, you immediately get that the original graphs are isomorphic. But if your complements are not isomorphic, you also immediately get that the original graphs are not isomorphic. So this if and only if means it goes in both directions. If you get to play with the complements and you can actually determine if your complement graphs are isomorphic or not, if you get a conclusion there, that means you will immediately get a conclusion on your original graph too. Now, that being said, complement graphs don't always work. So if we look back at our original two graphs, so now that we know about complemented or complements, or graphs that are complements, let us go ahead and find the complement graphs of these two guys. And I am now wishing I had also prepped up all of those vertices. So you're going to see how crazy it is for me to write vertices in a circular notation. All right, so to make a complement, we're going to copy the vertex set, and I'm going to go ahead and copy the vertex set exactly in the same orientation for each of these two graphs. So A at the top. We'll then have B, G. We'll then have C and F. We'll then have E and D at the bottom. Oh, that actually wasn't as bad as normal. Awesome. Now, when you go back in to put in the edges, you can't put in any edge that's in the original graph, and you want to put in all the edges that aren't in the original graph. So if we fixate on A, so we start at A, well, we can't put in A to G, we can't put in A to B, we can't put in A to F, we can't put in A to C, but we can put in an edge from A to E and A to D. Same deal with vertex B. We can't connect it to A or C or G or D, but we can go across the graph and connect B to F and to E. And notice since these two graphs are both symmetric, in other words, you can spin them and it's still the same picture, you'll get the same, we're going to be doing the same thing all the way around. So at C, any guesses who C should connect to? Yeah, that's basically it. Your insides between the two graphs are basically going to be flip-flopped. So yeah, C will connect to G and F. D will connect to A and then G. And double check, are there any extra edges we need to worry about? I think I got them all. All right, so then if we do the same thing with the other guy, again, attempting to put the vertices in a rough circle orientation, a little bit smaller than what I did on the other side. Oh no, I almost missed 6. There's 5. So this time we won't have the edges around the outside to form what looks like a polygon. You're only going to have edges in the middle. And in this case, if we look at vertex 1, who do you think vertex 1 should connect to? Hint, it won't be 2 or 7. Yeah, 6 and 3 looks correct. What about for vertex 2? Any guesses who vertex 2 should connect to? I see 7, yes. Not 7 and 5. Yeah, there you go. We'll be connecting to 7 and 4. Now, what about for vertex 3? It's already connected to 1. Who else should it be connected to? Yep, perfect. All right. Notice here, I know that there's only going to be 2 edges because in the complete graph, every vertex is connected to every other vertex, so the degree would be 6 all the way around. Currently, the degree in the original 2 graphs is 4, so that means we're going to get all of these guys to be degree 2 in the complements. In other words, 2 edges touching each of our vertices. So that's another behind-the-scenes things that you can think about. You don't have to think about that, but it's a way to make sure you're doing it right. 4 then would connect to, it should connect to 6. And it looks like we've got one more edge. 5 is connecting to 7. Do a quick double check, make sure I haven't missed any edges. Now, once you have your complement graph, just like once you have your subgraph, you're now focusing on those 2 graphs and seeing if they're isomorphic. Okay? So you'll do the same thing. You'll look and you'll say, all right, well, I need to check to see if the vertex set has the same number of vertices. Don't overthink it. You didn't change vertices, so there's still 7. And then you need to look at the number of edges. What do you guys think? How many edges are here now? Yep, there are now 7 edges. And then we'll check the same thing over in the other graph, and let me go ahead and label this one. This was the complement of G2. That is the exact wrong side of the symbol to put the colons on, but I'm not going to fix it right now. So did we have the same number of edges on the second graph? Did anybody count that up? You can. That works too. I was just thinking of counting them without being fancy, but either way, yep, we actually still have 7 edges over in that other guy as well. Okay. I also went ahead and put in what we already talked about, that in both the 2 graphs, all of the vertices have degree 2. Please note, if your original 2 graphs, G1 and G2, had everybody of degree 4, when you do the complement, you should still have all of your vertices have all the same degree, whatever it was after you took the complement. Okay? So subgraphs, again, will not help. Okay? Now, once we're at this stage, we start looking at this and we're like, well, what should I do next? I'm still trying to figure out if these 2 graphs are complements of each other. And unfortunately, they were not as easy as when we looked at subgraphs in that previous example that we had. So this is actually where we need to do another thing. So this is like repeating step 1 again. This is like repeating step 2 again. And this is like doing step 3 in this particular graph, in this sort of complement. So in the overarching graph, we're in that sort of step 3 where you're checking properties. We're, again, in that same step 3 checking properties, but now on the complements. Okay? And one of you previously had talked about paths or cycles or circuits. I think specifically you just referenced paths. In these 2 complement graphs, it turns out looking at things like a path is actually extraordinarily helpful. And typically people don't look at specifically paths or trails, they look at cycles or circuits. Okay? So for this one, what we're going to do is we are going to look for circuits. Okay? So if we are in that first graph, that complement of G1, specifically the one that has the letters A through G, let's find ourselves, let us walk around that graph and see if we can't start and stop at the same place. So I'm going to be super lazy, and in my laziness, I'm going to start at A. So if we start at A, where do you want to go next? Hint, you've only got 2 options. Sure. So if we go to D next, well, once you go to D, everything else is going to be forced because we're degree 2. Okay? So once we go to D, from D, we're going to go to G. And remember, we're trying to get back to A. Once we're at G, we have to go to C. Once we're at C, we have to go to F. Once we're at F, we have to go back to B. Once we're at B, we have to go to E. And woohoo, we were able to get back to A. Okay? So let us actually write down what we just did. So here we went A to D to G to C to F to B to E, and then back to A. Note we had one big, and I'm going to use a layman's terms here, one big loop where we started and we stopped at A, at vertex A. Could we have picked any other vertex? You better believe it. And we would still be going around the graph. Maybe we'd go around in the opposite direction, but we would still be following along those same edges. Okay? Now, if these 2 graphs, these 2 complement graphs are isomorphic, any guesses what has to occur in the complement of G2? Don't overthink it. You got it. You have to have, it has to be that complement of G2 has to also be just one big old circuit. This is actually a special type of a graph called a cycle graph, where it's just one big, essentially, loop, where you start at one vertex and everybody's degree 2 and you go back to the starting vertex. So here, pick your favorite number. Do you guys have a favorite vertex you want to start at? Hint, it doesn't matter. Sure. So suppose we start at 3. I'm going to circle it so we'll see it after we do our scratch work. And at 3, where do you guys want to go? Do you want to go to 1 or 5? Hint, it doesn't matter. Sure. So let's go to 5. Now, once we go to 5, everything else is predetermined or is forced. Once you're at 5, you have to then go to 7. Remember, you can't repeat edges in these type of guys. Once you're at 7, you have to go to 2. Once you're at 2, you have to go to 4. Once you're at 4, you have to go to 6. Once you're at 6, you have to go to 1. And we actually did make it all the way back to 3, which was our goal. Now, let's write that up. Oh no, I pushed the wrong button. So this one here, in the graph that's a complement of G2, we start at 3. So we went 3, then 5, then 7, then 2, then 4, then 6, then 1, then back to 3. And notice what we had in both cases. We had exactly one length. Don't reverse the T and the H in length. Length 7 circuit. Now, what does that tell us about the two complement graphs? Any guesses what conclusion we can get to? Yes to all of those things that you guys typed. So yes, in both of these two graphs, you could have reordered your vertices specifically in these orders that we just found, and both of them would essentially unfold and create what looks like a polygon or a big circle, except you use straight edges. Okay. In terms of a conclusion, we don't have a firm well, we sort of have a firm conclusion. There's a ton of evidence that says these guys should be isomorphic. Okay. Now, to actually get the final answer, you have to go ahead and write down the isomorphism. So here's how you grab your isomorphism. So conclusion. So the complements are going to be isomorphic because they're both just one big circuit. One big circuit. And that is going to imply that the original two graphs are also isomorphic. The only way that you can, wow, I put the complements in there. Don't put the complements in there. Wait a second, we're going to erase that. Ah! Only problem with that eraser is it likes to erase more than I want it to. Okay? Now, you do have to go ahead and give the isomorphism. I don't quite have enough space to write it there, so let's go ahead and write that next to these two graphs. Okay? And I'll move it around before I post it so it's not tiny. This isomorphism will work for either the original graphs G1 and G2. It will also work for the complement graphs. Okay, so since we have the complement graphs right here, right now, I'm just going to look at it off the complements. Okay, so first thing is just write down all of the vertices for one of the two graphs. It doesn't matter which one you grab. We went all the way to G, F, G. And then you look to see who you match to. Apparently, I cannot write an A today. Okay. Now, here's what you can do. You use your circuit. Okay. So here, A, we can match it to anybody you want. It doesn't matter. But once you pick who A is matched to, you have to go in consecutive order of this circuit, follow that same order of the second circuit. Easiest, since we started with A, just to match A with 3. Which means then B is 1, 2, 3, 4, 5 into the circuit. So 1, 2, 3, 4, 5, B has to be matched to 6. Or if you prefer, perhaps the easier way, D is the second guy on the circuit, so D and 5 have to be matched. Or mapped is the appropriate word. Third guy right here is G in the sequence. Third guy here is 7, so G has to be mapped with 7. C, fourth one in. Fourth one is 2. E is second to last. Second to last is 1. And I could actually not look at the circuits whatsoever and claim that F better be mapped to 4. And that's just by process of elimination. It better be that last vertex we didn't deal with. Roughly. So A here can be mapped to any one of the 7 guys, so that's 7 possibilities, but you can map it around the circuit either clockwise or counterclockwise. So in this case, there would be, 14 different possible isomorphisms. Let me tell you, that's super fun to grade. Not really at all. But it's nice in the sense that you got lots of options that you can do. But that is it for today. Sorry, it looks like I ran over time by a minute or so. Next time, We'll look at more stuff on isomorphisms and things that you can do. I've got another example or two that's similar to what we did today, and then some other things that you can do with identifying graphs are isomorphic or not. But like I said, that is everything for today. And don't forget, we have homework that's due today.